Okay, so for dealing with this question number 36 in the text, we're being asked to find the acceleration of these masses shown here. A couple of things that we have to look at. If m3 accelerates downward, then m2 and m1 will accelerate to the right with the same acceleration. If you notice, these ropes are taut, meaning that they're pulled tight. They're not sagging or anything. So M3 won't move before M2. Once M3 starts moving, M2 will move in exactly the same way, and M1 will do the same thing. So all of these accelerations will be identical. So that's one thing that gets shared. The second thing is we'll look at, we need to talk about directions, because once I figure out the forces that are acting on these and the directions that they act, the acceleration will come from that because we know the masses. So let's assume that the force acting on M3, gravity, will tend to pull it down. It should move down. M3 should fall, M1 and M2 should go to the right. So let's call this plus direction and minus direction. So down is plus, up is minus. It doesn't matter if it doesn't. I could assume that it's going to go up, and once I do the math, it'll work out. I'll just get a negative direction to be downward. And so now, because these ropes are tied together and the direction just changes, if M3 goes down, that means that M2 and M1 go to the right. So again, we'll call this plus and minus direction for M1 and M2. So sort of to the right and down is our positive direction, and to the left and up is our negative direction. So let's start with a free body diagram for each mass. So I've got M1. I'll have M2, and then last I'll have M3. So we look at this, and for M1 and M2, we'll ignore the force of gravity and the normal force because they'll be offsetting each other. Then they won't inform the motion in any way. We could include them, but we'd have to have them negate each other. We'll ignore that they're for now. So the only force that's acting on M1 to cause any motion would be the tension due to the first rope. So let's call this T1, and we'll call the tension in the second rope T2. So this is T1. Then M2, T2 will tend to pull it to the right, but the M1 will sort of drag it. It will create some drag, so it'll tend to offset it. So and T1 will be acting on M2 will be equal and opposite to the T1 that we drew for the first mass. And now, assuming that it is going to move to the right, then T2 had better be larger, or it won't accelerate. So T2 will go to the right. Now for M3, I forgot the 3 there. Force of gravity, of course, is acting down, and it'd better be larger than T2. So the force of gravity is acting like that. T2 should be the same magnitude as the other diagram, and we've got our free body diagrams that will set up the motion. Now, from the free body diagrams, we can use Newton's second law, that a net unbalanced force, which is the sum of all forces acting, provided it's unbalanced, will cause the mass to accelerate. So for mass 1, we can say that M1, let me do this down here, M1 will accelerate due to T1. That's the only force that's going to inform the motion. We'll call this equation 1. M2 will accelerate due to the difference between T2 and T1. Provided T2 is larger than T1, it'll accelerate to the right, and we'll call that equation 2. For the mass 3, M3 will accelerate. That'll be due to the difference in the force of gravity, which is M3 times g. There are 9.8 meters per second squared, minus T2, and we'll call this equation 3. And we'll use these 3 equations in the next video to solve for the acceleration.